Good morning, everybody. Today we're talking about conditional probability as we move along in our probability unit. And for the first time today here with conditional probability, we have situations where sometimes our sample space is being restricted. What I mean by that is, to this point, we've always considered the whole number of people that are participating in an experiment, or the total number, this number over here. But in this case, sometimes we're going to just be looking at specific aspects of data that we're given. So let's take a look. There's some terminology here. The probability that an event A occurs given that B has already occurred is called conditional probability. Okay, and the notation's right here. There's that vertical line, and the way you read that is the probability of A occurring given B. So the vertical line means given. So it means that you're looking at just the sample space of B and looking where A occurs within that space. So with that in mind, let's take a look at this experiment conducted at Sells Middle School. So there was an experiment with medicine and belly aches, so on and so forth, and we're trying to determine how reliable this medicine is. So there's a two-way frequency table there. We saw some of those last lesson. We're going to use them again here. So letter A says, to the nearest percent, what is the probability that a participant who took the medicine did not get a bellyache? A participant who took the medicine. So we're just looking at the people that took the medicine, and of those people, we want to know who did not get a bellyache. All right, so careful with your, just the way you're reading it and understanding that. So we have to consider the number of participants who took the medicine. So how many of those people are there? There's 65 of those people. 65 people took the medicine. We're looking at that column. And of those 65 people, 54 did not get a bellyache. So the probability of A given B, so the probability of a bellyache or no bellyache given they took the medicine would be 54 over 65. So notice how it's out of 65, the column total, not 100. So it's not out of the total in this case. And that fraction reduces to 83.1%. All right, let's take a look at the next one here. To the nearest percent, what is the probability that a participant who did not get a bellyache took the medicine? All right, so now we're kind of flipping the order here. So how many participants did not get a bellyache? 76. So now we're looking at that row total right there. 76 did not get a bellyache of the 100 total people. And of those 76 people, how many took the medicine? 54. So this probability is 54 over 76, which is 71.1%. So it's different than the previous one. That means something in terms of independence, these two events being independent from one another. But that is something that we're going to talk about more next time. All right, so let's look at how we can kind of express these theoretically, these different formulas here, A given B and B given A. So first, determine the n of A, so the number of elements in A, that was 76, the number of elements in B, 65, and the number of elements in the intersection of A and B, which is going to be 54. And I got that by looking at took medicine and no bellyache, and that's 54. Okay, so now it says express A given B and B given A in terms of n of A, n of B, and n of A intersection B. So the probability of A given B, our sample space was out of just set B. So that's going to be in our denominator. That's what we're considering. That's what we're dividing by. And over here, when it's B given A, we're dividing by the number of elements in set A, okay? And on top, we're looking at the intersection of those two sets A and B, which is going to be the same for both of these, regardless of the order, because BA, AB, the intersection is going to be the same number, which is the number of elements in A intersection B, and the same thing here. So you'll notice the difference between these two is the order of the letters obviously makes a difference in your sample space. So when it's the probability of A given B, then B is your sample space, notated there in the denominator. And over here, when it's B given A, then A is your sample space in the denominator. That is the difference between these two statements. Next, I just want to show you what's called a relative frequency table here. A relative frequency table is when we convert these numbers from the first example. We took the very same numbers in the table and we converted them to percentages as decimals though. So we got them, all these percentages or decimals here, by just taking the number in each of these boxes from the previous example and then dividing by the total 100 to get those decimals. Notice how our total is out of 1, which is 100%, right? And there also happened to be 100 people in the previous experiment. But in a relative frequency table, regardless of how many people are in the experiment, you're going to have a 1 there in the lower right-hand corner. Notice that these add up, and so the columns add up to the column total, the rows add up to the row total, and these add up to 1, and also these add up to 1. Okay, so all those things are going on here in a relative frequency table. This is something you've seen in the past probably, but maybe not for a little while. So all this is saying here is that these probabilities can be expressed as decimals here. And so we're just taking these very same pieces of data from the previous example and we're expressing them in decimal format. So that's what I wrote there in letter A and letter B. I just went ahead and filled out that information for us. The probability of A, no bellyache, was 0.76. The probability of taking medicine was 0.65, and the intersection of those two was 0.54. So I just wrote those in based on the relative frequency table. And then in letter B there, I'm just specifically spelling out how to calculate these probabilities as decimals here. If I want to find P of B as a decimal, I take the number of elements in B and divide it by the sample space S. S is the entire sample space. And the same thing for all of these. Intersection of A and B, take that number in that set of A intersection B and divide by the sample space. And then for the probability of A given B, you're taking the number of elements in the intersection of A and B over the sample space, divided by the number of elements in B, the second letter there of course, divided by the number of elements in the sample space. And when you conduct that division by multiplying by the reciprocal, converting that to a multiplication problem, what would happen is these cancel out and you just get this. It's just, I guess, adding a little context and understanding to how we calculate those probabilities. At this point in the lesson, it may be a good idea to take a look at these problems right here, pause this video, go through them, see if you can answer some of them. If you want to do that after I explain the ones that I've circled, you can also do that. I'm not going to do all these examples. I'm just going to do B, D, and E. And then maybe it would be a good idea to do A, F, and G. And then the key for this is on the agenda, so you could check it and make sure you're understanding well enough before you move forward. So the first three questions there, A, B, and C, are all more basic probability questions that you would have seen in previous years. So I'll do letter B just as an example. So the probability of drawing a jack. So consider how many cards there are in a deck. It tells you right there. So there's 52 cards, 4 of them are jacks. That reduces to 1/13. So that would be your answer for letter B. So there's no conditional probability here. It's just more of a basic probability question. But D and E get at specifically what we've been talking about today, which is the conditional probability. So D says the probability that a red card drawn is also a jack. So what that's asking you for then is the probability of a jack given that it's a red card. Probability that a red card drawn, that's how you know that that's going to go here, is also a jack. That's what goes there. Okay, so let's use our formula that we had derived previously in this mini lesson here. So to calculate that, I would need the probability of the intersection of J and R divided by the probability of R. which is the second one there, the sample space. So the intersection, what's the probability of a jack and a red? Well, how many jack reds are there? There's 2 over 52. 2 out of 52 are jacks that are red. And what's the probability of a red? 26 over 52. Now, if I conduct that multiplication, it would be, you would multiply by the reciprocal, the 52s would cancel. You would get 2 over 26, which reduces to 1/13. That would be your final answer. 1/13 would be your answer for letter D. Now, look at the slight difference here in letter E. And for letter E, I'm going to kind of show my work down here just because I ran out of space there a little bit. For letter E, the probability that a jack drawn is also red. So now the order's been flip-flopped. So now instead of the probability of jack given red, we're looking for the probability of red given jack. That's going to change our calculation a little bit, isn't it? That's going to be the same as the probability of the intersection of those two over the probability of a jack. So as I figured that out, the probability of a red jack is still 2 over 52. And the probability of a jack is 4 out of 52. If you conduct that division through multiplying by the reciprocal, the 52s would cancel and you would get 1/2. So notice how the difference in the wording completely can change your answer, doesn't it? Probability that a jack drawn, well, there's only 4 jacks, right? And 2 of them are red, so 2 out of 4. So a lot of this stuff can be figured out kind of just by thinking about it through logic. I showed you how to use the formulas to get your answers. But again, some of them you may be able to just look at them, think about it, think about your sample space, and figure out the probabilities. But I always encourage people to show work, to add a little further evidence for their answer. So that's that. At this point, I would encourage you to pause the video, see if you can do A, C, F, and G. Check the key on the agenda. If you don't need to, if you feel totally confident, feel free to move on. As always, sign up for conferences. If you need anything, please reach out. I miss you guys. I hope you're doing well, and talk to you soon. Keep it 100.